Yeah.
This meeting is being recorded.
Gibbs free energy of the liquid, and the green one for the crystal. The Gibbs free energy for the liquid is lower, so therefore the crystal cannot be stabilized. Okay. Okay. If we move a temperature lower than the melting temperature, so the liquid's temperature. So instead we have an opposite condition where the free energy, the Gibbs free energy, will be lower than so therefore the system, the crystal can be stabilized. Okay, and this delta G V, that is the Gibbs free energy for the volume, will be higher going a lower temperature. And this is connected in some way. We see in the next slides how this is connected with this. So this is the difference. That is the difference of the between the melting temperature and the temperature where your system is below the liquidus temperature. So therefore the subliquidus condition. Okay. So this delta T can be called supercooling or undercooling. Okay. When your system is undercooled or supercooled, means that you are below the liquidus temperature. So therefore, your crystal phase will be activated because the difference in delta G V. Okay. Great. Okay, we had one step. We define undercooling, that is the liquidus temperature minus the temperature at subliquidus condition. So therefore, you will have a certain delta GV. Okay, the delta GV can be written, just to be simple, in this way, where you consider the enthalpy and the temperature and the entropy. Okay, if you look at this diagram, you see that here you have the free energy, Gibbs, and then this is the temperature. More or less in this system, moving from above the liquidus, below the liquidus, the enthalpy will remain constant because you have the latent heat of the crystallization. What is going to happen is that the delta G will increase, as we said, and this one will increase. Okay, so therefore the increase of entropy will favor the formation of the nuclei. Okay, if we want to move from what we said to so far, so from this equation, just we can substitute this with this, and basically what we get that at the end of this equation we have that the delta GV can be written like the variation of enthalpy basically times a difference in this melting temperature and the actual temperature where the system is divided the melting temperature. So this delta T here is the delta T that we defined before. So this one, the undercooling condition. At the end, what you see that there is the relation between the delta T and the delta GV, as we said before. If delta T will increase, the delta GV will increase. So therefore, there is this relation. And this one, from thermodynamic point of view, is the driving force of crystallization. Okay? So therefore, if this is the driving force of crystallization, in some way, this is directly related to the driving force of crystallization. So therefore, when we work on our systems and we work on our phase diagrams, experiments, natural samples. It's quite difficult to calculate the delta GV and to say, okay, to quantify the driving force in this way. But what we can do for sure is to calculate this delta T, because it's related to the liquidus, and we can constrain the liquidus. We did yesterday. And if we fix the liquidus and we know which temperature our system is, so we can calculate delta T, okay? So therefore, this delta T is much easier to calculate for us, and can be considered the driving force for crystallization. And what is it? It's just this temperature minus this temperature as subliquidus condition. This is the liquidus that we constrained several yesterday for plagioclase, olivine, cranopyroxene, and so on. This is just the liquidus. Above the liquidus just melt. Below the liquidus, it's subliquidus condition where this phase will be in equilibrium with the melt. Okay, so the difference between this temperature and this temperature at fixed pressure, this difference in temperature will be this undercooling here. Okay, and how can we impose an undercooling to our system? So we can do cooling at constant pressure, decompression at constant temperature, or what it can happen during the conduit, you can have decompression and cooling at the same time. Okay. So therefore, you can pass from a condition above the liquidus to a condition below the liquidus, imposing a certain undercooling. Okay, and this undercooling can increase if the decompression will continue or if the cooling will continue. So therefore, it means that you, from thermodynamic point of view, you will increase the delta GV. So therefore, the driving force for crystallization. Okay. So in terms of nuclei, how do we stabilize a nucleus? So we have to reach a certain radius. This is the delta G. So therefore, here we have in negative the delta GV, and here the delta GS, that is the surface energy. Okay, and this is the total delta G. Total delta G, yes, where basically we can define a peak. The peak is representative of in some way, the energy needed to stabilize a critical nucleus, okay, a critical radius of the nuclei. And we see what it means. So we define basically a critical radius that is the energy barrier to stabilize the nuclei. If we don't reach enough energy, so that nuclei, the nuclei is just transient, can be formed and then dissolved. So therefore, we can now go from the nucleation to growth. Okay, can be just a transient. Okay, and just to simplify this, we can think about work. The work that has to be done to stabilize these nuclei. And so the W is just the work of the formation of a critical nucleus that corresponds on the energy released, basically, and the formation of a critical radius. This equation is, there are also the tension, the surface tension between the nucleus and the liquid, and the delta GV that we discussed before. So therefore, when we move from a liquidus condition, above the liquidus condition and below the liquidus condition, what is going to happen is we have to stabilize the nuclei in order to have crystal growth. And so what is going to happen here, that if you see the radius here, we can calculate the critical radius through this equation, that this is the tension, the surface tension between nucleus and liquid, and this is the delta GV. If we increase this delta GV, the critical radius will be reduced. So what does it mean in terms of undercooling? Huh?
So is the radius of the nucleus?
will be reduced. So therefore, it means that you have to have less energy, less work to stabilize the nucleus. To make it simple, what does it mean? It means this. We remember that delta GV is related to delta T. If I increase delta T, so therefore I decrease the temperature, okay, and I go to higher undercooling, what is going to happen? That my delta G will be higher, and so my critical radius has to be smaller. And so it means that also the energy that I need, okay, has to be smaller to stabilize the nuclei. So what does it mean? It means that if I'm closer to the liquidus, I'll need more energy to stabilize the nucleus. Instead, if I'm far away from the liquidus, it's easier from an energetic point of view to stabilize the nucleus. Okay?
And to destabilize it.
To destabilize, it depends. If you are, for sure, if you are closer to the liquidus, it's more difficult to stabilize a lot of nuclei. So therefore, probably you can form some of them, but so only of them will survive. Okay, in a transient. So therefore, when you need a lot of energy, it's possible that there is no nucleation, or it takes a lot of time, and then here we are going towards this equilibrium condition that I'll introduce a little bit later. So just this is how it works for homogeneous nucleation. We move towards heterogeneous nucleation, where, as we said, we need a persistent surface in order to minimize the energy, the surface energy. At this point, what we need to consider that the nuclei will be, the nucleus will be like this, okay? And it will touch the persistent surface. So therefore, having a persistent surface, the energy needed to form a nucleus will be lower. And also will depend on this angle. And we see what it means. This is a wetting angle. So first of all, I make a comparison in terms of energy between homogeneous nucleation and heterogeneous nucleation. So we need much less energy, and critical radius has to be smaller because you have already a persistent surface that reduces the surface energy for the nucleus. And this is the first point. So therefore, heterogeneous nucleation is much easier to achieve than homogeneous nucleation. What does it mean? If we want to relate with undercooling and our natural systems, our rocks, our magma, that if our magma is at low undercooling, very close to the liquidus of for instance, a plagioclase, the plagioclase probably won't nucleate on a persistent surface because the energy to form just an homogeneous nuclei is too high. So therefore, if there is a persistent pyroxene, the plagioclase will nucleate on the persistent pyroxene. Okay, that is what it means. Okay, the other point is this wetting angle. Okay, the wetting angle depends on the energy and depends on the undercooling, okay, and the delta GP. And so therefore, as we said, homogeneous nucleation means that we have a spherical nuclei, okay? So therefore, having a bigger angle here means higher energy. Having a reduced angle, wetting angle, it will imply less energy. And we can see this here. So in this diagram, here we have the surface energy and the volume delta G energy. If you see, this is the homogeneous nucleation, and the homogeneous nucleation will be related to the maximum energy needed to stabilize the nuclei and the maximum critical radius. So therefore, we need a lot of energy, a lot of work, and an important the undercooling. So therefore, the undercooling has to be large to have an homogeneous nucleation. Instead, nucleus with an intermediate angle will have an intermediate energy and crystal critical radius, and so the energy and the critical radius will be reduced, depending on the wetting angle. Okay, so therefore here you can see the nucleation towards basically the undercooling. So at high undercooling, stabilize homogeneous nucleus, and then reducing undercooling, the wetting angle will be reduced because I need less energy, and the radius will be, the critical radius will be smaller. All of this, it's at equilibrium condition. Okay, we have no discuss about time. Okay, there is no time in this equation.
What makes change the angle?
Is the angle will be changed based on the energy that you have, so therefore the undercooling. And if you have a large undercooling, it's possible to form, you have enough energy to form homogeneous nuclei. If you reduce the undercooling, you go closer to the nucleus, closer to the liquidus. Basically, what you have, you need some help. Okay, so persisting surface, and if you have basically very low energy available, it means that the wetting will be smaller. Because so basically what is happening that the wetting angle in some way is related to the critical radius. If the critical radius is small, the wetting angle will be smaller. It means that the energy that you need to stabilize that nuclei is smaller. Okay, this depends on the delta GV that is related to the delta P. So the distance from your liquids. Okay. We connect everything together.
So you connect it like cooling conditions to the shape of the angle,
yeah.
The angle, the stability.
Yeah, exactly. Okay. Now we introduce the effect of time, because so far we said, okay, this is happening without time. Instead, what we observed experimentally that when you move from a pressure and temperature condition above the liquidus, so therefore no crystallization is promoted. When you move from that condition to a subliquidus condition, a certain undercooling, okay, you don't have an instantaneous nucleation. Okay, nucleation will occur after a certain time. Okay, so this is called incubation time, and this incubation time is different for each mineral. Okay, so for complex minerals like plagioclase crystals can be longer than, for instance, oxide or olivine. Okay. And this incubation time depends on the undercooling. It can be much longer at low undercooling because you need a lot of energy. If you don't have a persisting surface, if you have a pure liquid, it will take a lot of time to stabilize a nucleus. If you have a large undercooling, so for a lot of energy, a lot of delta G, higher delta GB, it means that you can stabilize nuclei easier. It will be easier to stabilize nuclei, and so therefore the incubation time will be smaller. Okay. This is one aspect that has to be considered. And this is part of the disequilibrium, because if you think that, for instance, if you perturbate a basaltic system from high pressure to low pressure, decompressing, cooling the system, what is happening, that basalt can react quite quickly, moving a subliquidus condition, and crystal can be formed quite quickly. If you instead, if you perturbate a rhyolitic system quickly, it's possible that you basically have an obsidian. Okay, and this is why, because you have an incubation time, and the incubation time is related also to the viscosity of your liquid. Okay, so and basaltic magma are much faster in terms of kinetics and nucleation than rhyolitic magma. Okay, so that doesn't mean that the rhyolitic magma doesn't want to crystallize with the same perturbation of that you impose to a basaltic system. So talking about same undercooling condition. So if you bring a basalt and rhyolite, same undercooling conditions, with the same perturbation, so fast perturbation of the conditions, and the basaltic system will crystallize, the rhyolitic one no. It doesn't mean that that is the equilibrium for the rhyolitic magma. It's just that you need more time to reach equilibrium. Is it clear? So it means that the basaltic system will reach equilibrium much faster than the rhyolitic magma. Okay? Okay. Another aspect to consider that is always related to the incubation time is the amount of water dissolved in your melt. So therefore, this diagram shows the number density, so the number of crystals versus time, okay? And these are different experiments with the same melt with different water content. Higher water content here, the circles, and lower water content here, the triangles, okay? So what does it mean? It means that if you increase the amount of water in your system, you reduce the incubation time. So therefore, your kinetics will be faster and your system will reach equilibrium much faster, okay? So this is in some ways related to viscosity of the system. So the water will reduce viscosity and will accelerate the kinetics. So and the diffusion of elements.
And it's the same the other way around. If you increase crystallinity basalts, then you reduce the kinetics and behave.
Yes, you yeah, exactly. You reduce the kinetics because crystallizing a basalt, you push the liquid to be more evolved. So therefore you go towards andesitic composition. So therefore you are moving from a basalt to an andesitic residual gas. So therefore your kinetics for sure, you will change the liquidus because you are changing the thermodynamics, and so therefore, and also the kinetics. So everything will be possibly slowed down. Okay. So therefore, we move to this diagram that is a bit the diagram, simple diagram that summarize what we said so far. And here we have the growth and the nucleation rate here, increasing this way. And in this way, we have the undercooling that increases in this way, and the temperature, of course, increasing that way. So what does it mean? It means that this is the liquidus temperature. So if you are closer to the liquidus temperature, a higher temperature, you will have a smaller undercooling. If you decrease the temperature, you increase the undercooling, okay? So therefore, the undercooling increases in this way. So if we increase the undercooling, what does it mean? That a low undercooling, the growth will be promoted over nucleation because the energy to stabilize a nucleus and low undercooling, as we said, is higher. So therefore, or we have a persistent surface, or it's possible that we will have a small amount of nuclei, but crystals that are quite big. Okay? If we increase the undercooling, we move towards, we will have more energy to stabilize nuclei. So therefore, nucleation will be promoted over growth. And then I'll talk about this aspect more in detail later, but just here, this diagram summarizes that a low undercooling, you will have a few nuclei, but large euhedral crystals. Also, the crystal shape are controlled by undercooling. Okay, and we see in the next slide, why is that if I increase to intermediate undercooling, we will have more nuclei, and the shapes can be transformed in more
¿Qué tal?
skeletal, very large undercooling, where you have spherulitic textures up to that a certain point you have just lost because your undercooling is too large. That at that point,
Pero va a haber conexión.
yeah, there is a kind of information that is time, that you go too fast, higher undercooling, you will have just glass.
Okay.
Pero si es para que se conecte más gente, ahí sí. Be able to move anymore, so it means that you go slowly.
Sí, es que para ver si
if you go slowly,
me interesa, pero tengo el horario así un poco justo, entonces si lo puedo enlazar desde donde voy a estar, pues perfecto.
Entonces ahorita se lo paso como quiero.
Sí,
Okay.
Muchas gracias.
Sí, no hay problema.
Estás también conectado ahorita, ¿no?
Sí, estamos haciendo unas últimas cosas.
Sí.
That means that we went under cooling, not as fast as glass, but fast enough to produce those textures.
So for sure you reach very large.
Okay.
Yeah, exactly. So therefore, here we start to connect our phase diagram that we did yesterday, and looking our textures, we can say, okay, we are far or close to the limits. Okay? That the information that was missing yesterday to better constrain our rocks. Okay, another step. So we discussed about nucleation. Now we move towards growth, and we see how crystals, shapes, and crystal fraction will evolve once the nucleus is stabilized. Okay, here I introduce two concepts. One is crystal growth rate, so how fast the crystal can grow, and the other aspect that should be considered is the diffusion rate. Okay. The diffusion rate of the chemical components, of course, that are needed for the crystal to grow, that are required by the growing crystals. And here we define two types of growth. One growth that is controlled by interface, by the solid-liquid interface, that will result in euhedral, well-shaped crystals. And then a diffusion control growth, or diffusion limited growth, that can be promoted by a very fast growth, and diffusion rate is not fast enough as the growth. Okay, so therefore at the end this will result in skeletal dendritic spherulitic shapes. Okay, Then we want to define the degree of supersaturation, that is the difference between this one, the actual concentration of the chemical component in the liquid and the concentration at equilibrium at specified temperature and pressure. And how we calculate the degree of supersaturation is the ratio between the growth rate and the diffusion rate. Okay, if this ratio is small, so it means that the diffusion rate is much faster than growth rate. At the end, this will happen when we have a small undercooling, okay, and we produce at the end aeroidal crystal shapes, okay. So small growth rate, large diffusion rate, low under. This is controlled by small undercooling. At the end, we have aeroidal large crystals. Instead, if we have a large degree of supersaturation, where the growth rate is much faster than diffusion rate, and this is due to a large energy, so it means this will happen a large undercooling. So this will result in formation of skeletal, dendritic, and spherulitic shape. Okay? So it means that these kind of shapes here, large crystal, well-shaped, are usually controlled by low undercooling, slow growth rate, instead, and so condition, pressure and temperature condition close to the liquids. Moving from articular to skeletal, dendritic, and spherulitic, the undercooling will increase. So spherulitic crystal can be formed a very large undercooling. So usually it's a system that is cooling down fast and imposing a very large. Okay.
Or just compressing it fast.
Well, but decompressing very fast. I'll show you this later. Exactly. If we want to combine what we said so far yesterday, presenting the phase diagrams with this crystallization theory today, so we have this phase diagram for plagioclase, simple binary system where we have albite, anorthite. This is the liquidus that we discussed yesterday. This is the solidus. So therefore, a condition close to the liquidus will have aeroidal tabular shapes, increasing the undercooling. So the distance from the liquidus will have skeletal, then dendritic, up to spherulitic shape, a very large undercooling. So the undercooling, of course, will increase in this way. Okay. So here I reported also this, that was nice picture drawn by Thomas Shea several years ago, where he drew basically the shape of feldspar, pyroxene, and olivine in 3D as a function of undercooling, and the evolution in shapes moving from aeroidal tabular blocky shapes to prismatic, forming then this upper swallow-tailed shape in the intermediate row to more skeletal shapes for plagioclase at large undercooling, and you can see also the evolution of your pyroxene or olivine or amphibole. So this is nice way of so looking your pin section and say, okay, I see these shapes more or less, yeah, low, intermediate undercooling, yeah, low undercooling or large undercooling. So another aspect related to crystal growth is, and here we go towards some more disequilibrium conditions. We introduced the diffusion and how the elements are incorporated into the crystals, and the diffusion at the border between the crystal interface and the liquid. So here we have the crystal, and we have the component A that is the major component in our crystal, and the component B that is the minor component in our crystals. So in the liquids close to the interface that is growing, so we will have a depleted amount of the component A because it's going into the crystal. Instead, the component B that is less is the minor element in our crystal, so will be rejected and will be here we will have basically an enrichment of the component B close to the interface between them. So this can control that ratio growth versus diffusion. Okay, and what is going to form basically? It's here we have a real case where you have a plagiarized crystal with aluminum that is a compatible element, and magnesium that it doesn't go into the structure. The aluminum will be depleted in the boundary layer, so that layer that is controlling the growth close to the interface of the crystal, and the magnesium will be enriched. At the end of the day, if you do that with all your elements, trace and measure elements, you will have a boundary layer that will be enriched in incompatible elements. This will stop the growth. So that when you reach the equilibrium. So when you accumulated too many incompatible elements that you don't want, so the crystal is not able to grow anymore because there is no more good elements for the mineral. Okay, so therefore what you have this irregular shape with this boundary layer enriched in incompatible elements. Okay, that is when crystal growth will stop and you reach equilibrium. Okay, if the system will change again, so therefore from this condition, in some way magma will move to lower pressure or will cool down, so pressure and temperature will change. It means that this implies that the undercooling will change, okay? And crystal, your plagioclase, like an example, your plagioclase will struggle to grow as before. So therefore, what it is going to do, it will make a spike going to take the nutrients far from this boundary layer where the melt is enriched in aluminum, calcium, sodium, and so on. So so these shapes here, this stuff here, or this stuff here, it's because it's just the swallow-tailed growth towards a dendritic crystallization that is related to the fact that you have a boundary layer around your crystals that was formed in initial condition, a certain pressure and temperature condition, certain undercooling condition, and then the undercooling moved to a higher undercooling. So therefore, crystal growth will continue through spikes. Okay, going to find the nutrients. So here, this is an experiment that we performed with Rafael in 2018 and 19, I don't remember. So where we observed in 4D this kind of growth. So we have the first part of the experiment was 10 megapascal, 1150 degrees Celsius. So the undercooling here is 10. Okay, and here you can observe this pyroxene growing with a hydral shape through time. This is 30 minutes from the beginning. No, 30 minutes from the nucleation. This is 51 minutes from the beginning of the experiments. So therefore, there is an incubation time for this pyroxene of roughly 20 minutes. And then you can follow the evolution of the shape through time. Okay, this nice hydral pyroxene. Then after 90 minutes, we decrease the temperature of 20 degrees, moving the undercooling from 10 to 30. Okay, and what you can observe is the evolution of the spikes. Okay, because this pyroxene wants to find the nutrients far away from the boundary layer. Of course, here we cannot see the boundary layer, but this is the evidence that it cannot grow just close to the interface between the crystal and the melt, but it has to go far away, finding other nutrients, pure melt basically. And crystal growth will continue in this way. Okay, so therefore we move from a hydral crystal growth to a dendritic skeletal crystal growth, where the growth rate will be accelerated because crystal wants to find nutrients far away from the boundary layer.
So we see that the spikes are all oriented in the same direction.
Yeah.
What controls the change in the direction?
This is a good question. I think this is related to, in some way, the fact that, first of all, these spikes were formed from the corner where the energy is lower compared to a flat surface. So, and then they go straight to find elements. But if you can say, through time, there are more branches that are forming. The branches are controlled by, in some way, the energy of the crystal, and we measure also the best scattered, not the best scattered, the BS. I can tell you later. No, I don't remember the name. So the orientation of the branches, and they are basically reducing the energy, going in that way, and find the elements going with multiple branches, basically. And what you have, there are other papers that are published with ex situ view, so just classic experiments, that they prove that when you have this kind of growth and you leave the crystal for a long time, also this part will be filled. At the end, you will have, you will go back to this shape, but the composition in the middle will be different. But you need a lot of time. It's like, I can show you later if you want. It's a kind of re-equilibration, and I'll show you later these aspects. You can see this kind of growth. This is like an olivine. Don't remember which magma with these textures. This is a plagioclase. I'll show you also this evening for the talk, where basically also these experiments we perform together. Yeah, together. So you see that these skeletal plagioclase were formed at undercooling between 80 and 175 degrees Celsius, so very high undercooling, very fast perturbation of the system. I'll show you this afternoon how these experiments were performed. And this dendritic pyroxene nucleating heterogeneously from the plagioclase. So basically, this is the experiments, this is the experiments, this is the experiment, this is the natural case. In some way, we reproduced the condition of these minerals that are the plagioclase and pyroxene in the products of the Plinian eruption, erupted from Etna 1 to 2 BC. So here the same structure, the skeletal plagioclase, this dendritic, these are olivine, and then up to reach spherulitic crystals. These I produce experimentally in trachytic magma, playing with undercooling. These were produced also by cooling and decompression. And as you can see, basically these spherulites are formed by, so from a persisting surface, and the lamella are nucleating forming like an initial bow tie shape, and then through time this bow tie shape will be filled up to form these spherolytic crystals, and they are alkali feldspar. So this is in 3D, but you can see also in 2D. So you see there is some resisting crystal, and then or persisting bubbles. They can form from bubbles. Okay. Or some products can be completely fully crystallized with tiny crystals, skeletal, and so on. So that means very high energy. Okay.
But can you go back? Okay. No, one more. This can occur during in the point just before the eruption.
Yeah.
For the rapid explosion.
Yes. Well, I'm sure this afternoon. This afternoon, I'll talk about this. So I just mentioned to show some. And here, just to make clear that this is the simple phase diagram that we introduced yesterday, olivine phase diagram for stellate firelight, liquidus, solidus, and so on. So if so at the equilibrium condition, equilibrium condition, if we cool down the system slowly and we go subliquidus below the solidus, what we have basically it's at the end we form an intrusive rock. In this case, can be like a dunite, for instance. No? Just an example. If we instead we introduce this equilibrium, so if we do the same cooling part but quickly, so what we can have a crystal of olivine when we go in subliquidus condition where olivine and melt can be in equilibrium. But then if we cool down quickly from subliquidus condition to the subsolidus condition, what we got is the olivine, yes, formed here will be quenched, but all the matrix, all the melt that was in equilibrium with olivine will be glass. So it depends on time, on the time that we spend subliquidus and below the solidus, subsolidus conditions.
It's the difference between the cooling rate and the activation.
Right, exactly. That is a fight between
Different activation rates between the different crystals, like olivine and pyroxene, so you can generate mixtures that.
Okay. So what you said is actually the point. If you want to compare basaltic crystallization, so crystallization in basaltic magmas versus crystallization in rhyolitic magmas. So it's easier to form obsidian in rhyolitic magmas because the kinetics and what we discussed before is much slower than basalts. So if you take, for instance, pegmatitic melts, they are quite impossible to quench. So it means even if you go incredibly fast, you will form crystals because they are so kinetically active that Justin Bayreuth last year, I think they published a paper that they were able to quench the first pegmatitic melts because they invented a way to quench the sample in a crazy fast way. So it depends about this fight that you said before. So how quick you quench, you cool down your system or you decompress your system, how fast the kinetics will react. This will change the condition how to approach equilibrium. Okay, so before and from your perturbation to equilibrium, there is this equilibrium condition that can change depending on, as you said before, and temperature, pressure, phases, and so on, viscosity, water content. So exactly this is the example that I wanted to go. If I go from here to here quickly, this trachyte will be an obsidian. If I cross this condition slowly, possibly some of these phases will be activated, others no, because it depends on the ship time. If I go to here and I stay for days, like this trachyte reach the equilibrium after more or less 8 days, 10 days. If I'm here after 10 days, probably I'll have an intrusive rock because it will be completely crystallized. Okay. This is the way how to read. And then the other information is that if I move here to here, so therefore I'll induce several, I'll impose several undercooling, depends on the liquidus. So therefore, if we make an example, a realistic example, I stop here. So it means that between this point and the magnetite, I have a large undercooling, a lower undercooling for biotite for each phase, a smaller undercooling for pyroxene, a very small undercooling for alkali feldspar. So it means that it's possible that I'll have different shapes. I'll have different depending on the undercooling that I imposed, because the liquidus are at different temperature at that pressure.
Basically, you have an energetic magnetite.
Yeah, exactly.
Exactly.
Exactly. This information. So when you have your thin section, you can see and say, okay, I have this population of crystal. These are skeletal. These are oidal. So you can say something about where you are once you define your phase diagram. Okay. So the
You use the
yeah.
And the examples that are given, so we have different shapes, also different proportions.
Different proportion as well. Exactly.
So the more we can lead will be less.
The less if you are close to the liquidus, and more if you are more nuclei if you are far from the liquidus. The other point that you have to consider in terms of proportion, and this you can see when you run melts, that the composition can control the abundance of certain phases. So, for instance, this trachyte, if you go to see the composition of the bottom position, is not so far from an alkali feldspar. So, therefore, the dominant phase in this magma, if I go here, despite this low undercooling, the main phase will be alkali feldspar. Magnetite, biotite, and pyroxene will be much less in volume, because the composition wants to form alkali feldspar and not too many. So
comparing the mass fraction you have each minerals and the results of the simulation.
yes, you have.
That's the way you.
Yes, exactly. And yeah, this is good part. I go back here just to now I want to introduce. I want to show you some experiments that I performed on these trachytic magmas, and I did basically or cooling or decompression experiments, and I performed also some decompression and cooling experiments. We can see the effect of these conditions on alkali feldspar crystallization, and these are backscattering images, and these are basically alkali feldspar. The white stuff, the white dots are magnetite and pyroxene. Okay, here I reported these are experiments in cooling, these three, and this in decompression, okay? And here I reported the undercooling imposed to the system, so 19 by cooling, 39 by cooling, and 69 by cooling. So if you see the amount of, so these experiments were performed at the same time, so same duration. So here just you see a few nuclei of alkali feldspar, a low undercooling. A large undercooling, I don't know if you see, there are more tiny acicular crystal here, here. At very large undercooling is basically it's crystal mashes, mostly crystallized with a tiny spot of melt. Okay, so here you can see how undercooling controls the alkali feldspar crystallization. The same you can observe keeping the temperature constant, decompressing the system. So in this case, at undercooling 25, I have a couple of alkali feldspar, some pyroxene, and a lot of tiny oxides. And then increasing undercooling, I will have more alkali feldspar here, as you said. So the volume fraction will increasing undercooling because I increase the number of nuclei that will be stabilized up to undercooling 115, where is mostly crystallized, completely crystallized by alkali feldspar. So in terms of results, is this. So here I summarize the results. We have undercooling, and here you have the nucleation rate. Here the grow rate. The grow rate, you have to look at the dashed line, okay? And the nucleation rate, you have to follow the solid line, okay? So for increasing undercooling, I have first the peak of growth, and then the growth will decrease and the nucleation rate will increase. So what we said before, that from theoretical point of view, growth will be promoted mostly a low undercooling, okay, with a few nuclei, bigger crystals. But then if you move to larger undercooling, nucleation will be, you will have a lot of nuclei.
I have a question with the previous slide.
Yeah.
It's apparent or real, but it looks to me like the effect of undercooling is stronger during cooling than during the compression.
Yeah.
The last result of undercooling with cooling is more crystalline than the one with the compression.
Yeah.
Is it like that, or is just?
Yeah. We can see on the paper the crystal fraction. I remember that this anyways is highly crystallized. Yeah. Don't remember in detail, but they are quite crystallized, both of them.
Okay.
So I have some of them in the compression. I put these images. I have some experiments, some decompression experiments that you don't see glass.
Okay. So it might be just
the area. Yeah, the area. Yeah. Your question. Okay. Yeah, in terms of grow rate, this based on these experiments with the ex situ view. So I performed experiments, I quenched, and then I prepared the sample and I analyzed the sample using the sketching images. So I calculated the grow rate versus undercooling, and the grow rate decreases, increasing undercooling. And okay, and this is the Right. This is the same grow rate. This is for cooling experiments. This is for the compression experiments. Okay. So the behavior is the same. So grow rate decreases. No, this is also for time. Sorry, through time. Of course, the grow rate decreases through time because for what I said before. So you reach equilibrium. So the crystal will reach, basically will create the boundary layer that full of incompatible elements. So therefore you reach equilibrium and the grow rate will decrease unless you don't change the conditions. But here I didn't change the condition. Just one condition, one pressure.
So it's a kind of chemical saturation.
Yeah,
So
exactly.
the grow rate is proportional to the.
Yeah, exactly. Stop. Okay.
And how do you get the value of the grow rate? How do you measure it?
You measure like this. Basically, you select the crystals, the single crystal, and what I did, you measure with image J the length. You can measure the length and the width if you want. I measure the length in 2D. Okay, and I selected the 30, 40 larger crystals in the sample. So, and what I do an average of the largest crystals. Then I consider also the other population. I do an average grow rate, considering all of them. Of course, the assumption is that using the largest one, and this we will discuss later, using the largest one, this was done in 2013 during my actual PhD. This I did during 2009, 2010. The assumption was that if you take the larger crystals, it will be the first that nucleated. And therefore, then at the end, when you take the length, you have to divide by time. The time is the duration of the experiment. So taking the larger crystals means that possibly you take the crystal that nucleated at the beginning of the experiment. So therefore, dividing the length by the time, you have the grow rate. So an assumption that the smallest crystals are possibly nucleated after is the assumption. You see that it's more complex than that. Maybe I can introduce this now, because with Rafael, between 2016 and 2019, we performed several experiments with this furnace, Zali's furnace, where it's ambient pressure furnace. You can reach 1250 degrees Celsius. This is the heating element here. You have two thermocouples here, and the sample can be located here. So basically here, within the furnace, close to the thermocouples. The sample, we use basically a basaltic, we study basaltic crystallization, and we put a basaltic glass into a crucible, in an alumina crucible. The alumina crucible was put here, and this is a rotation stage. This rotation stage allows us to rotate our crucible during the experiments. We need rotation because we combine high temperature experiments at ambient pressure with X-ray tomography. I'll introduce better this afternoon. I don't want to say too much about that. But this furnace has basically two windows, one here, one on the opposite side. This allows an X-ray beam to pass through and to pass through our sample while you perform the experiments, and then you can acquire images. So the attenuated X-ray beam can reach a camera that takes the picture. And you can take picture over time, and you can make basically you can record like the video of your experiment. So I want to introduce you this experiment here at 1150 degrees Celsius. So we started at 1250 degrees Celsius for half an hour, then we decreased the temperature, and then we kept 1150 degrees Celsius for 4 hours, and then we decreased the temperature at 0.4 degrees per Celsius. What I'm going to show you now is what is happening here during these 4 hours through this video. The video is very fast, but the duration is 4 hours. Okay? So if I can do that. Okay. Okay. This is the crystallization of pyroxene in 4 hours in our Etna basaltic glass. Okay. Show you again. Yeah. We have a nucleation, heterogeneous nucleation of the pyroxene from here we have, this is the crucible, basically. It's a cylindrical crucible. Maybe you can appreciate better here. So it's made like this, okay? We have at the beginning an heterogeneous nucleation. Since this glass is in contact with air, we have a surface in contact with air. This surface is a good surface to reduce the surface energy. So therefore, heterogeneous nucleation occurred at the surface with air, and then mineral pyroxene were able to grow in this direction, as you can see. Okay. Then we have nucleation, heterogeneous nucleation from the crucible. So the contact between the melt and the alumina crucible, because also crucible reduce the surface energy. And just after 150 minutes, we observe, at least what we can understand, it's a homogeneous nucleation in the middle of the sample. Okay. So therefore, I have this video, maybe that should work. That can show you how, yes, a bit. So this is the crystallization at a certain point of the experiment. How, so there were some pyroxene growing from the top of the crucible down, some pyroxene growing from the crucible inside, some spherulitic growth, some homogeneous nucleation after 150 minutes. So here we were able to calculate the crystal volume fraction for the oxides and for the pyroxene. Okay, so basically after 240 minutes, so the pyroxene was more or less 8%, so 0.08 crystal volume fraction. Instead, oxides reached 0.18 more or less volume fraction.
So you start with a basaltic composition.
Yeah.
And you get
Pyroxene and oxides at 1150 degrees Celsius ambient pressure after 4 hours. This was the amount of crystals that we
use an intermolecular buffer.
this no yet was the experiment the year after, when yes, yeah, we didn't have any buffer. In fact, we formed a lot of oxides.
And so the rest is the matrix.
Matrix, it melt, just melt.
But how do you set the buffer?
Here there was no buffer, it was ambient pressure.
And with the buffer, what do you?
What we did, we put basically a nickel foil around the sample, and we tried to buffer the. In fact, when we put nickel buffer, oxide we were not able to form anymore. So oxygen fugacity changed the mineral assemblage. So And we did that because from a segmentation point of view, when you want to segment, when you want to get and isolate your crystal, so the black area that you see here is just melted and oxides. But to reach that point, when you isolate your mineral phase that you want to see from the rest, particularly if you have tons of tiny oxides, make your segmentation very difficult because there are several algorithms that you work with in order to decide the grayscale that you want to select in your tomography images. And it's not so easy. So the four oxides were a problem for us at the end to segment our phases, and we want to remove them. And we use a nickel buffer in order to avoid them.
It's very good. That's why I thought.
No, yeah, I worked on this for 4 months to reach this point. Every day.
Because I mean, they can also influence your heterogeneous.
Exactly,
They use oxides to do.
For sure, we observe a lot of heterogeneous nucleation from oxides when you reach here, this point, a lot of nuclei were forming, nucleating on the oxides. Yeah, a lot. So therefore, this what I wanted to show is that this crystal number density. So here we are counting the number, okay, through time for pyroxene. This is pyroxene, okay, and we have this heterogeneous nucleation at the beginning related to what I said before, the crucible air and so on. And possibly some oxides. Then I wrote, yes, after this event, we have another event where we observed homogeneous nucleation. Yes, homogeneous nucleation here. So we observed some crystals forming from the glass, from the melt, sorry. Here, and then we have another heterogeneous nucleation related to the branching of the crystals. Well, we observed that they were basically growing from pre-existing crystals, and then so you see that we have this onset of heterogeneous and homogeneous nucleation. Then the numbers went down at this point. It doesn't mean that you have dissolution. It means that they start to coalesce crystals. Basically, they are attached together when we count them. So if they are attached together during our segmentation, you cannot separate anymore. So they are. So therefore, this doesn't mean that the number didn't increase, but just that they are touching each other. But what you can see after that, you have another pulse of nucleation, and then you have growth. They touch together, and then another peak, another peak. So what it means here is that also from here you can see this crystal nucleation rate that oscillating through time. It means that nucleation is not just one event at the beginning, like we introduced before. So you impose your undercooling conditions and you have an incubation time, but the incubation time doesn't mean that it's valid for a unique event. You have multiple events where therefore you have a multiple incubation time. It depends. Some phases, some crystals can nucleate just at the beginning of the experiments because the energy surface is enough to do so, but it doesn't mean that this will stop the nucleation that you have just one event. You can have multiple events in time.
And what would be the longest case when you can? How long can the experiment? How long can you perform the experiment? How long?
Here we perform just for hours, as much as you like. The synchrotron is quite difficult because usually you have between 3 and 5 days. So therefore, what you want to do, you want to perform a lot of experiments.
Is that, I mean, if you have this repetition of different stage, or like, maybe there is a cyclicity to study there.
Possibly.
Like, I mean, you see that you have evidence, but it's
Yes,
really
possibly up to reach the equilibrium.
interesting to get
Yeah.
it there.
Very long, yeah. Possibly, yeah. Possibly, yes. And here we didn't reach the equilibrium for pyroxene. You can see in this diagram. In this diagram, you have the crystal volume fraction versus time for the pyroxene and the oxide. And the dots are the data obtained by from our experiments. And the line is the calculation with melts. Okay, this liquidus, this line that represents the evolution of crystal volume fraction at the equilibrium condition was calculated basically with melts and combining melts with equation that we developed for basaltic magmas that considers the disequilibrium of each phase. And so what you can see is that the equilibrium at 1150 degrees Celsius should be achieved around more or less 500 minutes for the pyroxene and less time for the oxides around here. And then basically you don't have more growth, okay? And so, and we reach equilibrium for the oxides, more or less. Instead, pyroxene didn't reach equilibrium. So therefore, as you said, if we perform the long experiments, we observed basically more nucleation evidence and more. So to reach equilibrium, basically, we had to reach around 14% of crystals. Instead, we reached around 8% of crystals. So this means that equilibrium there is a local equilibrium. There is no a wall equilibrium for your magma. It depends on your phases and the distance from the liquidus. So and the kinetics. So the pyroxene didn't reach the equilibrium in our experiments. The oxide, yes, after 240 minutes. This is the message as well. So some phases can be in equilibrium, other phases maybe not, in terms of crystal abundance. Okay. Do you have a question about it?
Are you going to show us how to do something like this with melts?
So for sure we can calculate the equilibrium.
Yeah.
Equilibrium, yes, we can do this. This equilibrium is a little bit more tricky. And then I don't know how familiar you are with crystal size distribution. Crystal size distribution. Heard? Okay. This can be useful. Okay. Crystal size distribution was developed, I would say, from Marsh, I would say, in 1988. Yes, 1988. And then Higgins published several papers at the beginning of 2000, late 90s, how to use crystal size distribution. And in this distribution, basically, there are the concepts that we discussed so far. And it's a good method to extract kinetics and time scale from our textures. so using 2D textures. So, and we have this relation between the population density of the minerals that you are considering and the crystal size. And usually you have this relation, and the intercept of this relation, here you have the nucleation density, the nucleation rate, okay, and the nucleation number density. And the slope is related to basically the growth rate of your phases and the residence time of that population of crystals a certain condition at depth. Okay, so therefore, this technique can be used to calculate how long a magma can stagnate at depth. Okay, so this is very important for pre-eruptive conditions, or as we will see, semi-eruptive conditions. Because what we can do is we can track the evolution of the population of certain minerals, certain crystals within the conduit. Okay, so the idea is this. You have a magma chamber and conduit. Magma stagnate here, and several population of crystals will be formed. And then you can, if you analyze and quantify your 2D textures, measuring the amount of crystals and their size, you can have this relation. Okay. So basically, what does it mean? It means that if you look this andesite, there's a classic andesite, the porphyritic textures where you have a phenocryst, microphenocryst, and then if you go to see in the matrix, you have macrolites. Here you have a 3 population of crystals, particularly. For the crystal size distribution, you don't need to consider all the minerals. You have to do a calculation for one mineral. So in this case, we use I don't know, if you want to use plagioclase or you want to use pyroxene, it doesn't matter, it depends. The point is that you are consistent with your analysis. If you consider the plagioclase, you will have this phenocryst, you will measure the size and the numbers of this phenocryst, and the microphenocryst and the macrolites on the matrix. These represent 3 stages of crystal nucleation and growth in this magma. Okay, so therefore, what you need backscatter images first of all, where you can segment the phases. So therefore, you can segment plagioclase as a phenocryst. If you are not able to resolve the microphenocryst and the macrolites, you take images at higher resolution and higher resolution until you segmented all your phases. Okay, so therefore, in this case, for the Calbuco samples, I had 3 populations: the phenocryst, microphenocryst, macrolites. I segmented all of them. What you get, basically, once you segmented, it means that you separate your phases to the rest. Okay, and then there is an algorithm developed by, you combine ImageJ with this algorithm called CSD correction developed by Higgins in late 90s, where at the end you can get this relation. Okay, and this relation means that you have a small amount of big crystal, a bit more of phenocryst, a lot of tiny crystals. Okay, and if you want to, you can split these in 2 slopes. Okay, this and this, or in 3. Depends how your distribution is. Okay, so therefore, usually porphyritic textures show 2 or 3 slopes, and the slopes depends, as I said before, on the growth rate, on the time scale, and the nucleation density. So the slope, so representative of this population, will have a much higher nucleation density than this. So it means that the number of big crystals are much smaller than the macrolites, and the slope will be different. And if you measure the slope and you know the grow rate of your phases, so therefore, if you take grow rate literature for plagioclase, you can enter in this equation here. So where your incognita is time. You want to know how long, for how long your magma stagnated there. So therefore, at the end, you will be time equal -1 g per slope. And if you know the slope, you know the grow rate of the phase that you are considering, okay? At the end, you get time.
So you have to do it with each change.
For each, yeah, exactly. Because you will see that the residence time for these minerals will be years, for instance, or months. This one will be hours or days. The intermediate will be something in the middle, weeks or months. So this is usually what we get. So it means that, and then you can correlate, okay, this is probably the stagnating in the magma chamber for years. This can be the activation of the system. This is the conduit, because they are perturbating fast. The system is perturbating fast, the undercooling will increase. And if you see, now you see, look this shape here and look this shape here. This is the same mineral. What do you think the undercooling is, where the undercooling is higher at this point? You know now. So you know that here the undercooling is much higher than that. So it means that this was in the chamber, this is this was produced in the conduit.
Wow.
Exactly.
La autoridad tiene una cantidad de microlitos impresionante, entonces nace en su muy rápido. De la autoridad al domo de 13.000 años.
De 3.000.
13.
¿Conmigo?
No,
Ok.
la erupción de 13.000 que
Ya.
grupo de bloques ceniza.
Ya.
Y coincide con la denunciación. Ahí tengo en el cajón. No. And how do you choose the growth rate?
The growth rate?
Like from the literature, how do you?
Okay.
I guess it would change.
Yeah, it changes. And what you need to do is you have to consider the experimental works that were performed with the similar magma that you are considering, and calculating the grow rate for if you are considering plagioclase, you take the grow rate of plagioclase in that melt. And for instance, there are a lot of data for basalts, for plagioclase and pyroxene, in andesite as well, basaltic andesite and andesite as well. A little bit less now. They are increasing a bit in dacites and rhyolites, but there are as well. So, like if you look at Hammer paper, Julia Hammer, or there are a lot of Rutherford, or if you look the Bristol group, you will find a lot of data on the andesite and Montserrat, and but there are.
So the assumption is that the growth rate is co-depending with the chemistry of the melt.
Yeah.
And undercooling is not affecting the growth rate.
So what you can do is to take when I do these kind of things and I calculate the residence time for these kind of minerals that are quite irregular and so on. And this one, what I'm going to use the fastest grow rate obtained large undercooling. So I select the grow rate from the experiments. Because if I use fast grow rate here, it's not realistic because it's clear that these are riddle growing slowly. So therefore, I have to take the slowest undercooling compared to this one where the control is limited by diffusion. So therefore, I know that they are growing fast in one direction, and the grow rate.
It's for basalt, the basalt growth rate for basalt planet. Like plagiaries in basalt, and check then there's some experiments or theoretical value for high undercooling or low undercooling.
Yes, you will have it. So you will have it. So if you look at the, I don't know, let me see if I have some real example. So these are experiments that I performed on Stromboli basalt. And yeah, these are all the conditions with all the undercooling. So these were fixed temperature decompressing experiments from 100 megapascal to 50, 25, 5, and 5 megapascal. So therefore, the undercooling will increase so from 24 to 97. And then I think I reported. I hope that yes, I reported the grow rates. So these are the values that you want to take. Okay? And if you see more or less, they range between 10 to the minus 7 centimeter per second to 10 to the minus 8 centimeter per second. Some of those 10 to the minus 6 centimeter per second that are the fastest one. The fastest one usually are they coincide with the short duration of the experiment, and then I'll talk later why this is true. Because the growth is the peak of the growth is just at the beginning, and I'll show you this afternoon better how it works. So therefore, you can select different order of magnitude, and if you test 10 to the minus 6 and 10 to the minus 8, you will have a very big change in residence time that will go from hours to years, basically. Depend on the slope then, but this is what you get. So therefore, then you have to select exactly the right condition that you want to, that can be representative for your slope and for the population that you are looking at, and selecting so wisely the grow rate, because it has to be representative of that kind of distance. But there are tons of experiments at this point on that.
And I have another question.
Yep.
The experiment you do, you measure partition coefficient of elements with different places.
Yes.
And is there a relation between these partition coefficients with elements and the growth rates? I mean, is the growth rate influencing the partition coefficient? Like,
Okay.
compare.
So good question. I have this paper published in 2018 where I perform exactly what you are asking to me. Around 3D melts, considering alkali feldspar. Okay. And so therefore, what I observed that there is a diffusible equilibration through time. So if I perform very fast experiment, so trace elements will behave in a certain way. And then if I keep the same condition longer, so I'll see that there is a diffusion, a re-equilibration. So therefore, I constrain the equilibrium from track height doing that. And what you observe is this. I don't know if it's useful for you. Yes, these are the case feldspar that I produced, and I analyzed the measure and trace elements along, so between the crystals and the melt. For short duration experiments, like 2 days, And long duration experiment, if I remember correctly, is around 1 week, 10 days, something like this. Okay, so therefore you have the same crystals, but then the trace elements, the distribution of the trace elements is completely different. So there is a high accumulation of incompatible elements at short duration, because what I said before, if you remember the incompatible layers, the boundary layers, there, when you have the selection of the compatible elements and incompatible elements, so the incompatible elements are enriched in the boundary layers. This is true at equilibrium condition, but if you quench your experiments under this equilibrium condition, you will see that if the crystal growth is fast, crystal will take whatever it takes. It brings into the structure, okay, and randomly, enriching also non-compatible elements. So you will have incompatible elements in the defect of the crystal structure. And then if you wait time, there will be a reequilibration. But if you quench at the beginning, you will see that you can form like a barium alkali feldspar, because you will have a lot of barium inside that it doesn't want to be there at the equilibrium condition, but just the growth is so fast that it's taking everything, and then it reequilibrates after. So, and you can see basically, I think I reported.
So at the beginning, all depends on the velocity of the kinetics.
Yeah, exactly. What we discussed before, that ratio between growth rate and diffusion rate, that is valid for the measure elements, but also for the trace elements.
If you have fast enough kinetics, equilibrium might be just an illusion.
Yes, exactly, exactly.
Okay.
But this it can in some way constrain the time scale. What I did in this paper then at the end to constrain the time scale for Campi-Flegrei, because you have a lot of eruption. You have alkali feldspar of Campi-Flegrei that have a layer that is barium enriched, and I was wondering why. And the reason possibly is that you have a very fast growth, a very fast perturbation, fast growth, and then it doesn't equilibrate. So it means that since I reached the equilibrium after 8 days, it means that if you have a barium enrichment in the natural sample, it means that it didn't reach 8 days at that. So it means the perturbation happened and then erupted. Before the, yeah, that is surprise. This is what we get from this experience, and yeah, I don't know which one, I don't remember. So here you see this the partition coefficient. This is the long duration. This is the short duration. The black one are the short duration, and the long duration. And you see that the partition coefficient for this is this is strontium. This is for strontium. This is for rubidium and barium. So rubidium is not affected too much. Yeah. The particular barium that is if you see from the structure of the yeah, you can see. So barium is one of the incompatible elements, trace elements that in some way can enter easily in the structure. For that reason, is in the peak of the coordination 2. So therefore, barium can be is in the site of potassium. So therefore, can be the substitution. Yes, but rubidium and strontium are quite a little bit far away. And then you have here all the trace elements. But also, if you see, the trace elements will behave in the same way, will be enriched in the short duration, will be then removed during reequilibration and long duration. Yeah. And we, at the end, we remember where I put the equation. Yeah, this I calculate this equation for the time scale basically, based on barium and strontium. You can calculate the time scale if you want. If you measure your partition coefficient in alkali phosphate in trachyte, is valid for trachytes. You can calculate if you reach the equilibrium or not.
We can calculate time between crystal fermentation and then eruption. Let's say, if considering that it didn't achieve equilibrium.
Yeah, exactly. At least this works quite well for that. So I don't know if I answered your question.
Too many information.
Sorry.
I need to connect the dots.
Sorry.
No.
But it's recorded.
See.
It's recorded. So.
I don't know what that means.
Time to break.
We are almost finished by
Like the short time experiment is the like a fast growth rates, and we can see the partition coefficient and the faster growth rates,
yes.
and the long term like higher time experiment, duration experiment. It's like would be the proxy for the slow way.
Sorry, can you repeat? Sorry.
Because my question at the beginning was: is there a relation between growth rate and partition coefficient?
Yeah.
And the last figure you show me is partition coefficient as a function of the time of experiment.
Yes.
So if it's a short time experiment.
Yeah.
Short time experiment with fast growth rate.
Yeah.
Would you say that it was fast growth rate with the short one?
The short, yeah. Yeah, for sure. Let me see if I put. Okay, this is a good question. I think I calculated, I guess. Let me see if I did. I remember that I did, but yes, growth rate is here.
Okay.
So this is growth rate versus partition coefficient.
Well, see, this is...
yes, you see that basically this is the long duration. The long duration. So based on the same growth rate, I know.
There's no effect on the growth rate.
Okay, but how it works, this one? Because there is an information that is missing here. That which one is the long duration? And the long duration though are this one. Are this one here, the long duration. The slower growth rate. So therefore this is the fast growth rate. They have a coefficient partition that is higher.
Short duration.
Short duration is this one with the faster growth rate.
So fast growth rate is as the what's the x-axis?
The x-axis is 10 to the minus 7.
The growth rate.
And instead the long duration is 10 to the minus 8. So therefore is growing like this. It's going like this from slower growth rate, long duration to short duration, fast growth. So yes, there is a relation between growth rate.
For the short experiment, if we only look at the short time experiment, the difference between the data points. In X is the growth rate. So I mean the one that is on the right side is higher growth rate, and the one that is on the left
is a low growth rate.
Okay. So for similar short time experiments, samples that have high growth rate as partition coefficient. It's flat. I mean it's flat.
Yeah.
So if it's flat, there's no there are no dependence on the growth rate and partition coefficient.
The short duration, not really.
Okay.
Not really. So this is the same order of magnitude of growth. It's 10⁻⁷. You change the order of magnitude here.
Okay.
10⁻⁸.
See the scales.
It's more or less you are within the same flow rate. It's not going to change too much.
Okay.
Because the size of the crystals and the duration of the experiments is quite similar.
Thank you.
Welcome. You want to take a break?
Yeah.
Right.
Okay. So before, once you get this crystal size distribution, you can calculate the slope. The algorithm, so the software that is called the CSD correction. Like if you go on Google and you put, let me see if it works. CSD correction begins. Yeah, this is the website. So yes, I think you have to download image J, of course, is this one. Image J is this, and then there is this is CSD output that is a plugin for image J. I don't remember if I have here or not, but if you go to plugin, basically it should appear here. I don't have in this version. But if you put this plugin of CSD output, you will find it in image J if you put as a plugins. And then once you get this image, you will be able to, in image J, to calculate this curve using the CSD output that you install in image J. You will get this, basically. And what you need to know is the aspect ratio of your crystal. So if you have an individual crystal with basically you have to put the short and intermediate, the long axis in order to say, okay, my crystals are more or less like this. And then you calculate, you will get the values and the diagrams. You will get exactly this one automatically with the slope. You can calculate the slope directly from the equation, from the program. Yeah. And there are some, the last version, there are references. There is the book of Higgins talking about this. It's published by Cambridge University Press. And the three main papers of Higgins. And it's explained how to do it. It's quite straightforward now.
So you just need them to analyze the image.
You have to analyze the image. Yeah. Then you calculate the population with the output, and you will get that. Then you calculate the slope. And basically, changing the slope, you change the residence time. So if you have this slope, for instance, very steep slope, the residence time will be slower. So comparing the same flow rate, of course, decreasing the slope, you will increasing the residence time. Yes, you increase the residence time. Yes, exactly. So decreasing the slope, you will increase the residence time. And of course, going in this direction, you will increase the nucleation density because you are going to touch basically higher nucleation density. And
so for example, if you only do it with microlights, You forget about any time space, but you get the residence time inside the conduit, assuming that everything is formed periodically.
Yeah.
And then the slope is like this, you could say time will be shorter.
Yeah.
And the same if you only consider phenocrysts and forget about the microcrystals.
Yeah.
You will get the residence time in the probable magma chamber.
Exactly. So basically the split would be like this. If you have a curve like that, you will split into slopes. This representative for the microlights and probably the conduit. This is the magma chamber, longer residence time, shorter residence time.
But do you need to do that directly on your image, like only segmenting the phenocryst or only the crystals, or the CSV program will be able to do the separation?
You will get this, and then you will separate, saying to the program, I see the slope that is in these 3 points, so these 4 points, and then you calculate the slope, and the slope, if the curve it fits well the points that you selected, so therefore, okay, you say, okay, this is correct, and then of course this cannot be fitted with this, so and you will select maybe this, and then you will calculate this in the program. Then you can select what you want, and you say, okay, calculate the slope and consider this.
Save time segmenting crystals if you are only interested in the time in the magma chamber, and you don't care about the conduit.
Yeah.
You don't just segment the phenocryst quickly.
Yes. Absolutely, yes.
Okay.
You can consider just that. Exactly. Yeah, this is the example that what you can get if you have, for instance, a magma chamber with a thermal gradient. So from hot zone to a chilled zone close to the margin, well, you will expect that since you are in a hotter condition, if we assume a distance from a liquidus, the hotter condition will be closer to the liquidus, so therefore less crystal but bigger. This is the slope. And then if you go to a large undercooling, so here we are linking this slope with undercooling basically, and the same you can do in the conduit. So before the decompression, during the decompression, and during the placement, where cooling also will affect the crystallization, will move from less crystals, slightly bigger, to a lot of crystal tiny, and so therefore the residence time will change, and according also to the undercooling. Okay, before the decompression, after the decompression, you will have large undercooling. Outside, you will, also cooling will increase the undercooling. So therefore, we can put everything together. So if you calculate the slopes, you can think about these processes as well, considering the undercooling and how fast crystal can grow and the shapes and so on. Yeah, of course, then this depends on the crystal content. The higher is the crystal size, and the higher the popular number density, the higher will be the crystal content, for sure. And so therefore, here you have two information: crystal content, that is crystal fraction basically, and the number of crystals. And if we consider these two aspects, so crystal fraction and crystal number density, and we put in a diagram where here you have the crystal number density related to nucleation basically, and the crystal fraction that in some way is related to growth. So increasing the crystal fraction possibly this is due to the growth-dominated process compared to very high number of crystals that is related to nucleation-dominated processes. Here, this diagram puts all together experiments at different undercooling, lower than 40, between 40 and 70, 70 and 100, 150, 100 and 150, 150 and 200, and higher than 200. So you have this trend with the evolution of the shapes from rectangular prism to skeletal to dendritic and so on, as we said before. And so the increase of crystal number density and crystal fraction. If we do this with experiments, for instance, or if we start from evidence from natural samples using this kind of diagram obtained from experiments, what you can do is to better understand which processes are controlling activity. Here we have the same diagram with number densities versus volume fraction for different eruptions. So the crystal number density and the volume fraction here is calculated for plagioclase, for products of Pinatubo, Mount St. Helens, South Hill, and so on. And if you can see, Mount Pinatubo is here, high intensity explosions, so dominated by possibly large undercooling, forming a lot of nuclei. They don't grow too much compared to other eruptions where possibly are less explosive or lower intensity. Here they were collected lower intensity activity, where crystal fraction is higher and the crystal number density is low. So therefore, possibly here we have something related to not very large undercooling or something that growth is dominated, and this can help us to, in some way, to link our texts with the crystal content, number of crystals, and the thermodynamics behind that. I would say this afternoon I'll talk more in detail about that. It's more complex than this, but this can be a starting point to see things. And then my talk will be about this afternoon.
The competition between growth and nucleation. We saw the shape of these curves in the picture. Does it change? Is there cases with the type of minerals? Instead of plagic, we do the same thing.
Yeah.
Is there a big change, or is it have the same homogeneity?
It doesn't change what is the content, or
like, I mean, when you have, if you do the, I remember you showed a long time.
you mean,
Like a resume.
yeah, this one.
So this is like for any type of mineral, you will have this same shape.
Yeah, that is theoretical, but yes, it's related to undercooling. Yes. Yes. According, of course, with magma composition, you cannot compare in absolute terms crystal fraction and crystal size with plagioclase and, I don't know, a biotite in a rhyolite, because possibly plagioclase will be more abundant than biotite. So you have to always relate in relative terms, considering that things, not in absolute terms. Okay. because some phases, like I showed you before for the trachyte, alkali feldspar is the dominant phase. The rest is A4 as a few percent, but the alkali feldspar will change completely the geology of that mine. It's the dominant phase. So therefore, yeah. In relative terms, yes, it works. In absolute terms, like in the alkali feldspar, will be the dominant one in terms of abundance. Okay. I stopped here for crystallization. Okay. I had too much information. But now we can connect the phase diagrams, atomic phase diagrams, consider the water, CO2 solubility, phase diagrams, and the kinetics behind. So we see the phase diagram at equilibrium condition, but then there are kinetics processes that how to reach that point. So melts give us the end point. So it's the equilibrium condition. So the stability of that phase at the maximum time needed to reach that condition. Melts doesn't tell us what is happening between the initial condition and the equilibrium condition. So what is happening? I try to explain today, and then to link how Texas records this equilibrium in terms of Texas, abundance, shapes, and so on. Okay. Then I think we have finished. If you want, we can move to melts and do some other calculations. We try to compare equilibrium crystallization versus, we can try to do some fractional crystallization, fractionating solids, and we see how these affect melt evolution, melt differentiation, and the possibly the mineral chemistry. So for like the anotime number in plagioclase, how this will be affected. Okay. I'm in my from Okay. What we can do is we can run one simulation with the same basalt that we used yesterday. So with this, we can run one simulation with considering equilibrium crystallization, so what we have done so far. And the second one, selecting here, if we go on option, we have the possibility to fractionate solids. And what we can do is we can track the evolution of lipids. And we can compare if we see any difference between equilibrium crystallization and fractional crystallization. Yes. And we can do this with this basalt that is quite primitive, and then we can run it, for instance, with an andesite, and we see what we get doing this, and we see how far our liquid can be differentiated considering the two type of crystallization. And so what I'm going to do is this. I upload what I used yesterday stuff, and there was bars. So therefore we have these. Okay, we can remove the water. Can do an address. Remove the water. But it's easier. We do the intensive variables. This point, yesterday we selected very narrow range of temperature. Allora, we keep 1350, maybe we go to, we see if we go to 1000, can go also lower, 950 for instance. We do a very wide range, we see what we get. Thirteen fifty, 1350, and 950. Okay, we keep 1000, it's okay. 1000 bar. The increment every 1 degree. Okay. Let's see. And now I normalize. Okay. And we run this. And we are going to run considering equilibrium crystallization. So what we did so far. And we will have the results. Okay. Okay. Can open. We can actually we can save it. This bar this melts out. This we can call it buzz equilibrium crest. Okay, this is a buzz. So I put here. Yes, I save it because we can compare with the other one later. Once you get the result, you save it. You put in one folder, whatever you want, and we run the other one. So to compare. So we run the same magma, the same condition. So the same condition, exactly everything the same. Yeah. The only things that we add is a fractional solid. So this has to be selected. Yeah, the rest is the same. Yeah. At this point, you will decide how many crystals will be fractionated, how many minerals will remain in equilibrium with the melt, and we do normalize, and we run. Now we take also this one. This we call buzz fractional crest. Okay. Can open this. We can open both of them. Fractional crystallization, the equilibrium crystallization. Now, what we can compare, for instance, temperature 1150 for both of them. Okay. If you take the same, the same temperature. If this is the fractional crystallization, yes. So basically, after 1150, I have cyanopyroxene, plagioclase with 62 anorthite, and then all the phases fractionated. Okay, and the liquid has 50 0.1 silica, and alkali 3.23, 1.54.
First formation of the pipe.
1150 selected.
1150.
Yeah. So 1350 is just liquid. And if we go to see the same results at equilibrium condition, equilibrium crystallization, so basically stabilized the olivine, carbon feldspar. We didn't have olivine with the fractionate because olivine was completely fractionated. And the liquid has 49.7 silica, 3.13 sodium, 1.58 potassium. And there's instead here slightly higher silica, slightly higher, and we don't have olivine. And the feldspar has 62 anortite for the fractional crystallization. This is how much? 62. They are similar, more or less. Similar, slightly lower for the feldspar to use the fractional crystallization. Okay, we see some changes, small changes, but still the total solid so far 1150 is not so big. So the total mass in equilibrium with this magma is 1% basically. So therefore these minerals didn't have a big effect on the liquid. So therefore we can go 50 degrees lower, 1100. $1100 here, 1100 for the equilibrium. Okay. So the difference between the two is that this at equilibrium conditions, we still have olivine, cyanopyroxene, feldspar, spinel, something weird. And the total mass for solids is nearly 80% more or less. Okay. For the fractional crystallization, since the crystals were removed, okay, we have much less solid in equilibrium with this liquid, and the liquid reached 59 as a silica. Regarding instead the equilibrium one, the silica is 57. So we start to see some changes in the residual liquids.
Solids, they are accumulated mass fraction of solid. This is the fraction utilization, like the addition of all the small fraction.
Yeah. Yeah, exactly.
Even get the fractional crystallization with something else.
Oh,
So I
really?
think I miss one step or something.
Ah, which step?
I don't know.
I just repeated
procedure.
everything, just clicking fractional solids.
Yeah, I did load the data
Yeah.
with the pressure temperature parameters.
Yeah.
Then click on the fractional solids, normalize and run.
Did you need
Or I
the
get
water?
something different.
Is there water?
Yeah, without water.
I put without water, yes, I'm running without water, just to simplify.
Sí, sí. I will do it.
Yeah, I can wait for you. Is the water here is 0, just to make it simple, because when you're going to crystallize a lot, the fluids will be released, and the calculation is a bit. It's easy to see in this way.
Yeah, water is in 0.
Yeah, water is 0. Easy to see there the evolution.
Why do you have to train climate?
Because they stabilize 2 different pyroxene.
Okay.
So you see that one is diopside 33. And clinonestatite 24, Edinburghite 25. There is a way to calculate then the amount of diopside estatite. Instead, this is different. Is more a clinoestatite. Possibly this is more an orthopyrite. No, this is more epigenite. This is more neogite, more or less. Yeah, also feldspar in alkaline magmas, melts will stabilize 2 types of feldspar, because in feldspar you have plagiarized, you have feldspar. You have to read then the composition to see which one is which. In generally melts called feldspar, all the plagiarized and feldspar, but then you see the composition that is different.
Did you put the power?
Legal side.
Did you set it up? Yeah.
Sorry?
Did you set up the buffer?
I left what we used so far, so you used that from a new answer. I used just the same file that we used this. Yeah.
That's 1100.
This was 1100, yes. Yes.
Not the same.
This is fractional crystallization. This
Yeah, just do it again. Different.
is different.
I don't know.
The fractional crystallization. This is it, yeah. Okay. And now what we can observe is what is happening at 1050. So here is fractional crystallization 1050, and the same here, 1050. That's great. So with the equilibrium crystallization, we reach silica 60.5. With fractional crystallization, silica 65. Okay. And here still the mass, the solid mass is still very low because mostly it's fractionated behind. And it was left behind. Here we are really close to the solidus. It's 91, 92 weight% of crystals. The total solids for the equilibrium one. So it means that possibly now if we investigate 1000, it's possible that the equilibrium crystallization reached the solidus, you see? Yes. So therefore now the liquid this see already we are in the solidus, so therefore we cannot compare because we don't have the liquid, if you see. It's not so therefore we have to go higher in temperature and see where the liquid, the last liquid is 1004 degrees. Yeah, is it? With this is 62. If we compare 1004 as well, this 1004 for the fractional crystallization. At the end, fractionating everything in equilibrium with the liquid remains 1000. Fespar that is more albedic than anorthitic, is the anorthite number is very low. Is almost actually, if you see sanidin is 15, is an anorthoclase, is a kind of alkali fespar basically. And the liquid is 69 here. So we enter into the dacite composition. We are really close to be a rhyolite. If we consider instead the equilibrium crystallization, we cannot go higher than an andesite, basically. And then our rock is completely crystallized. So therefore, the difference that I introduced yesterday in diagrams, how you pass the peritectic point, you reach the peritectic point through fractional crystallization, because you physically remove the crystals, and what you get is the liquid. The liquid can go farther in its differentiation. Of course, it depends how much magma initially you have. Because if you have a tiny amount of magma and you fractionate it, you fractionate the crystals, the residual melt that you will get will be a really tiny amount.
There are some things that
or you have a big magma chamber at bottom. So this the point to what I want to introduce is this maybe. Because this was the question yesterday of Matthias, right? Yes, you asked me, how do you do that in nature? That's good point. So I'm going to present what I said yesterday to Mattia. Is this? So the idea is to have something like this. Like a mash-dominated reservoir with several lengths of magma and differentiation within the reservoir. How you get fractional crystallization? You have fractional crystallization through yes, this one. You have separation of crystals by density. So you have In a basalt, it's possible that olivine will sink down and plagioclase will float, and so therefore you will have a differentiation of liquid through time. What I was saying now is that if you have a big portion of basalt, at the end, if you fractionate and you will accumulate liquid at the center of this magma chamber, starting from a completely liquid basaltic magma, you fractionate the liquid, forming like a mash, and you accumulate the liquid here. Basically, you will accumulate an andesite, and this andesite, if we continue to crystallize and you fractionate solids, at the end you will have a core of rhyolite, like we did now. Now, to do so, you need a huge amount of basaltic magma initially to have an eruptible rhyolite at the end. If you start from a small amount of basalt at the beginning, so it's possible to do so, but then at the end, I think you will not have any eruptible rhyolite at the end. That is the reason why I think it's difficult to explain big rhyolitic. You have to have a big portion of basaltic magma to differentiate. Like what you showed yesterday, that linear eruption is incredible for the amount of magma produced. So it means that you should have a big differentiation of depth, but it means that you should have a big reservoir to produce dacite and rhyolite.
What's the time scale? What's the time scale to differentiate there?
That's a good question. I think it's not so fast. So
no, because I was wondering, like in mid-ocean ridge, we have big magma chambers.
yeah.
Fast spraying ridge, because never get rhyolite
No.
andesite, so the time extraction is too fast.
Exactly.
But when I'm thinking about it, like eruptions are also frequent.
Yeah. They also was you mentioned is interesting because in the ocean ridges the thickness of the crust is quite small, so you don't have a complex reservoir like I showed you before with different lengths, but you have a possibly 1-2 magma chamber that will form the gabbro, and yes, you can have some differentiation, but it's difficult that you will get a rhyolitic composition. And instead, it's likely that you have an environment like this one, like the subduction zone in Chile, in Mexico, Chile, or Peru, that you have a thick continental crust. You can develop a very complex reservoir where differentiation can. I think it's in terms of hundreds of thousands of years. It's now so at the end. What I was saying, maybe I'll introduce this also on Friday when I'll talk about for the experiments, that filter pressing, so forming a mash and then squeezing this mash, it's basically a mix between crystals and melt, where if you squeeze the crystals, you remove you squeeze the liquid basically out from the mash. Basically, that's a way to physically separate the two phases, or otherwise the other one can be flow differentiation, gascent, or mostly doing gascent, where you have accumulation of crystal and the liquid will move on because different density, contrast, and so on. So therefore, there are magma chamber processes that are not so fast to differentiate. But with maths, you can calculate if you have a big amount of liquids from basaltic magma. Actually, you can reach rhyolitic composition just with fractional crystallization.
So if someone, for example, wants to do a model with when you have to recharge your magmatic chamber, the idea would be to do one simulation get the residual liquid,
Yeah,
add some of the previous initial composition,
yeah,
and
rerun again.
rerun again.
Yes,
This will be like sort of approximation of
Yeah.
recharge.
yeah. And you will see how also the the composition of the minerals will change. Because now going in towards the acidic composition, you see that the type of minerals, the composition of minerals change accordingly with the condition and the composition. So at that point you have a dacite, and with this dacite with a very high sodium and potassium, plagioclase, anatomic plagioclase is not more stable, and you have this kind of you are in the corner between plagioclase and feldspar, basically, as an albite close to an orthoclase.
But at the same time, as we mentioned, you will remelt the solid phases that are in the
Yeah. Yes.
So we have to take the residual liquid and mix it with the new basaltic composition.
Yeah.
We have to take the top, well, or is it not just the same? It's the same.
Yeah. Is the unique way to pass the peritectic point to discuss. So this one. So it's the unique way to go further in your composition. So therefore, this is just a simple, but it's like we start from basalt and we move towards like a dacite. So now we do so only through even if we start from a very mafic basalt, that in theory we should not go here. At the end you go because you actually can go of the phases.
If you use melts and instead of doing the remove solids, you remove liquid, I think it is, then you track the composition of the remaining mush.
In some ways, yes. I tried to use it. I never understood how it works, to be honest, because it gives you something that is not straightforward. So therefore, I cannot tell you exactly, because I use sometimes, but I never understood what is giving to you. If you want, you can try, but we can do a test. So we do a fractionation of liquid.
Because it says fractionate liquids, fractionate fluids. You know.
Fluids? You mean fluids or liquids?
No, I mean what liquids, I guess, is the melt.
Yeah.
And fluids?
Fluids is the water and CO2 that you put.
Okay. So if you fractionate fluids, you end up with an hydrogen. So,
yes, because what you do is when you do equilibrium crystallization and you have volatiles considered in the part composition of water and CO2, the melts will re-equilibrate with that composition, that pressure and temperature, the water and CO2 that are in equilibrium with that melt. Okay. If you fractionate the fluids, the liquids, the fluids, yes, what you do is that you remove from the higher temperature to the lower temperature, every step, you remove the fluids that are going in the bubbles. So it's like it's outgassing.
Yeah.
And so therefore it's an open system. So therefore at the end you will end up that you will reduce slowly the amount of volatiles available. And you go for sure under water under submerged condition. Yes. So if you want to do that, you can do it.
This software can do reverse crystallization. You can take like the composition and to get back to the primary acidic composition. You take the rhyolite and you do the reverse crystallization.
Well, no, you can explain me better. I
Like-
don't understand.
You take the rhyolite.
Yeah.
And you calculate the acidic composition. Basically.
Right.
Right. You're considering the
You cannot go back. You cannot go back because when you go, so the rhyolite represents your rotative point.
Mhm.
So it's the end of the evolution. So if we take also this one for this, I don't know where I have. This one, yes. So basically, your rhyolite is the end of the magma differentiation, and it represents the rotative point. Farther than that, you cannot go. So therefore, if you start from a rhyolite, that you are at the rotative point as a composition, you will remain here. You will not go back.
Sure, but it was in case we want to calculate the composition of the source of the composition of the magma.
I understand
and
what you
lay
mean.
the rhyolite.
I understand what you
Is
mean.
it possible?
Right.
To do it with that?
Right. I understand what you mean. Okay. The point
This
is,
would be reverse crystallization by the simulation.
but
Like with the composition of the red.
together with that liquid, you need to have all the mash produced, all the fractionated solids that you, because otherwise,
All the phase of the system.
yeah, if you take all of this, okay, you can go back. But if you take just the liquid, now you stay there. Because you reach the rotative
So-
point.
We don't have, even if we have all the parameters of the system, final state of the system, we cannot, even with some constraint on this, we cannot do it right.
No.
Possibility.
And
Do reverse crystallization, considering this fraction of solid, this fraction of liquid.
from the right, no, no. Because what you consider is the new things that you can do. It's starting from like an intrusive rock. If you, for instance, with equilibrium crystallization at 1000 degrees Celsius, more or less, we reach the solidus. So basically, we form an intrusive rock with olivine, cranopyroxene, and plagioclase. Okay, so 100% solid here. So basically, what we produce is a gabbro. Okay. Now, if you a gabbro with actually with the residual liquid at the end, that is more andesitic. Okay, but that liquid is in contact with the minerals that we produce, is not separated, okay, is there. So therefore, if you start from that bulk, you simulate melting, you will go back to the initial composition, yes. But when you fractionated that, and you have to start from the entire bulk, so the liquid that you fractionated and the solids. Because if you select just the liquid, we can try, but you don't go back. You stay more or less there. Particularly if you reach rhyolite composition, it means that you are in the rotatic chemical point, basically. But more than that, you don't go. Yeah, in theory you can do that. So for instance, for my trichites, I did.
It would be useful to calculate the concentration of parental magma to see if there's a change in the mantle source composition of that volume system.
Yeah. what you need to consider is all the fractionation, all the fractionated parts as well. Because if you take just a liquid, no, it's like a
Would you
different system.
generalize of magma chamber?
You can
For
add
example,
more
if you have a-
Yeah. Yeah. Yes.
And the pomis, then it's the market. Combined.
Combined together. Yeah. In fact, the parental magma is not always easy to.
No.
So the primordial one is not easy to.
I was asking if it was the magic show. I don't you were
No.
calculating.
No, because you have three, in reality, in nature, you have three main processes. One, fractional crystallization, that at the end will give you just the final liquid. Magma mixing and assimilation. If these are key working together, I'm not sure that you can.
We have started this evening or each middle phase of the study, we have the Gibbs. And then the entropy volume.
Yes, exactly. I say MELS calculates the minimization of the free Gibbs energy as we discussed today, more or less. So the equation part, you have G, you have H, you have S, and it's calculated like this. So in fact, for MELS is able to calculate also in this data, thermodynamic data, are combined also with the experiments, where there are experiments in basalts. There are a lot of experiments, so for the results that you get are quite reliable. If you move, for instance, towards pantelluritic magmas, like alkaline rhyolites, is much less precise. So because based on the thermodynamic variables, is able to give you when feldspar should be formed, when biotite should be formed, when cranopyrite should be formed. It doesn't mean that it's realistic. It's a pure thermodynamic calculation without any constraint.
Is it good for the whole alkaline suite or?
Yes. Yeah. Particularly the rhyolite MELS, yes. Then at the moment I'm testing with my PhD students for the trachyte and phonolites. And some phases are comparing with experiments. Some phases like cranopyroxene is correct, plagioclase is not so far. When you go to alkali feldspar, it's a bit more tricky. Leosite is difficult. It depends which phases. Biotite, usually the hydrous phases, there are not so many experiments on biotite and amphibole. So therefore, can give you an estimation, but then I would not bet that is the right.
No, so I was interested in testing the biotite rhyolite actually yesterday.
Right.
Two rhyolites. One is amphibole, the other is biotite gross sodium albite.
Yeah.
But then maybe the biotite.
I don't know, we can test and see if it works. possibly it can give you some idea to say, okay, this condition biotite should be stable, in this condition instead ornament should be stable. It doesn't mean that the temperature is exactly correct, liquidus. So maybe it's 50 degree lower or 50 degree higher. Yeah, but if this is stable or not, maybe it can give you this. Maybe we can test this. If you want to test other conditions, if you have questions.
What's up?
Today a lot of information. We need to digest a bit. Yes, I'm cautious about that. We started slowly. We're building up.
I don't understand the first day how we determine if it was saturated or unsaturated.
Okay. So this we can do, if you want, we can do now. Let me know. I can give you, to make it simpler, I would say I want to provide an Excel file by email. I don't know if I have your email. Let me see. Yeah, could you send me email to all of us? I will reply sending the Excel file. So I can provide an Excel file from the Moore model that is very good.
Sí, ¿me lo dices? Ajá, sí, sí te tengo. No, me equivoqué. Matías, tu correo.
VM, VM, o sea, de Matías.
Ahí tengo. Ajá. ¿Correo? ¿Era de Benítez? A ver, checa porque muchas cosas.
Nada más como dividida la primera.
Sí, esta lluvia, no les va a tocar.
Then
Yeah, it's coming.
la lluvia. And this. And this. And okay, send four Excel files. We can open this one, the H2O solubility.
Do you have the file?
Maybe I sent it now. So I sent four spreadsheet. One is for the solubility of water. The Giordano viscosity. Do you know the model for viscosity?
Yeah, well,
Huh? Okay. This model is in Excel. You can calculate the viscosity of your liquid, different temperature and water content
Ah, okay, yeah.
condition. Then a density calculation. You can calculate the density of your magma. And the last one is a task. How you make a task? So very simple. You open and you go in data. You put your value of silica, sodium, potassium, and then they will plot. You see where you are. Basically, if you want to see quickly, is a way. Terms of solubility. This is the solubility model that I presented the first day, and is exactly, I can tell you. When I introduced this Jacobino classical model, the program that is putting all the models together. What we are using here is the Moore, the green one, the Moore model. That is very good for a wide range of compositions. So basalt, andesite, rhyolite, and dacite, and so on. In a wide range of temperature and magmatic pressures. Okay, so it's quite reliable. And you can close this one. This one. See the notes. Okay, if you open this, you have to do enable macros. Okay. Then you go in input. In input you have very simple. You have the pressure that you want to investigate, the activity of water, the temperature, and your composition. Okay. So we can just copy and paste our composition from silica to potassium. Just we copy from here. If we do you have this?
Sì, button active.
Doesn't work for you? With the Excel version. Okay. What we want to do is just so the philosophy is this one. What's this? Okay. Okay. We can copy the composition that we used so far, the basalt. Okay, here we put 49.97, 1.87, 15.98, 11.09, 0.2. Magnesium is 6.84. Calcium is 9.82. Sodium is 2.96. And potassium is 1.12. Okay. Okay. This is a basalt. Now, what you want to investigate is the solubility at fixed temperature. Of course, if we increase the temperature, solubility will be slightly lower of water. We put 1200 just as an example for basalts, and we assume just the only water in the system, no other system. So here we leave one. And then what you want to change is the pressure. So therefore, what you need to do is, you want to create a cube solubility cube. We can investigate several pressure. You can start from 2000 bar, for instance. Okay, 2000 bar. And after you put 2000 bar, what you need to do is to calculate solubility. And if you go to output, now you have a lot of numbers, but the last one basically is this one. So this is the pressure, temperature, and the last one is the amount of water dissolved in the melt. Okay? So this probably it's macro it doesn't work. Are you Rafael? Does it work?
I want to isolation or archivo.
Asignar macro.
No, cero archivo.
En Windows.
With the basalt, yes. With the basalt, yes. So here is the
Desbloqueado.
Sí.
Bueno, dice.
temperature was
1200.
Yeah.
4 point, okay. So basically, if you want to have a curve, what you need to do is just to put several pressure, like I do 1500, 1000. You click every time. Then you do 500. You click, then you do. Yes. It's 100. You click, and then you do 10. Click and 1. Click. Basically, you have all the list.
Sí.
Sí, verdad.
Sí. Sí, sí. La misma.
24. Ya no
Ah.
pasa.
No, 2019.
What you get at the end if you investigate. You put all your pressure and water content together, you can make a sorbidity curve as a function of pressure. So exactly what. So that this model, of course, is calibrated on experiments. What you get is your solubility of water for each pressure for that composition fixed temperature. If you change the temperature, of course, it will change a little bit, but not too much. If you increase the temperature, the solubility will decrease a little bit. If you decrease the temperature, the solubility will increase a little bit, but it's a minor effect. So the shape, the behavior of your solubility cube is this. In this way, you constrain in a simple way the maximum amount of water that can be dissolved in your melt. That is, I think, is the best approach. Then you can use melts. You can do the same, but melts. What it's going to do, since it is calculated also crystallization, at the end you will have. In this case, I put to 1200 degrees Celsius in order to consider just the liquid melt. With melts, if you start to play with temperature, crystallization will occur and your melt will occur. So therefore the solubility will change because your melt changes. So if you want to know the solubility of your bulk composition, maybe this is the straightforward way to do it. Just to have an idea of the maximum amount of water that you can. Melts, you can do more complex calculation, also considering CO2 together and calculate the pressure and temperature in melt.
Maybe we can repeat.
Yeah. Tomorrow we do a brief introduction to experimental petrology.
We went to fresh.
Yeah, exactly. So I have two options. So I have 2 lessons left. So experimental petrology using ex situ. So classical, I would say, furnaces with the ex situ view, where you have to quench and then look at the sample with the microprobe and so on. And then the other lesson that partially we introduce also today in my talk will be 4D an approach with the 4D experiments, so recording in real time your experiments, so looking at the processes in real time. So, or we can do all of this tomorrow, and then we leave Friday to repeat things to go through. We can start from the beginning and do all the procedure from that.
Pure exercise.
Pure exercise,
that's a good idea.
if you prefer, and we see where we get. And tomorrow I'll basically
All the experiments.
all the experiments I'll introduce tomorrow. Yeah,
Yeah,
so it will take at least 3 hours, I guess.
Yeah, that way also they can do all the experiments.
Esatto.
From the beginning.
Aprender,
Ok.
ya instalato.
Sounds good.
Estoy peleando.
Bueno, muy bien. Pero ya la noche cenamos en mi casa. Después te mando, ¿puedes? ¿O vas a ir?
Doy las clases de los martes y todo. Como que algo de decir, ya puedo.
Muy bien, muy bien. Después te mando la... Digo que es aquí. O así la mitad.
Nos cambió de casa. No me acuerdo.
Pero
Era
igual
el
te
primer
mando
año
la-
y ahí agarrabas.
Es aquí, sí,
Sí,
No digo que no sirve tampoco.
¿Tú nunca?
Sí sé qué colonia es, pero
Sí, que no.
4 minutos.
Con la motoneta, 5 minutos. Con el coche más. No, aunque está aquí de arriba, como si fueras a Santa Rosa. Ajá, la última colonia. ¿Dónde está la comer? La acaba de abrir. Oye, Martín, pensando, ya van a abrir un Walmart, es un infierno. Algunos dicen Walmart, otros dicen, espera, te saludo aquí. No, perdón. Nos vemos.
Hasta
Nos vemos
luego.
en la tarde al seminario,
Hasta luego.
a las 5, en el auditorio.
Perfecto.
No escucho nada. Ya que pongo yo el... Ya. Ah, no.
Los de
Chao. Entonces,